So in the last video we defined the pressure volume work, which is work associated with chemical change due to the disappearance or formation of a gaseous substance. So let's consider the first condition, that's a free expansion process. A process is considered a free expansion process when the gas expands against a zero opposing force. So when the gas expands against a zero opposing force, the gas is inside here, and this is the valve is left opened and the gas expands. In such a situation, the W given by minus P external dV equals 0, because P external is equal to 0. So in a free expansion process, no work is done. So usually this kind of expansion occurs when the system expands into vacuum. So in vacuum, where there's nothing present. According to the first law, if it's a closed system, the change in internal energy is just equal to Q. That is if Q is not equal to 0. So another process is when the gas expands against a constant external pressure. So in such a situation, W, which is the integral from state 1 represented by V1 to V2, P external dV negative. So because P external is constant, it can come out of the integral, and we are left with Vf minus Vi. So I apologize. This is V1 is V initial, and Vf is V final. So the work is just minus P external delta V, where delta V is change in volume, and it is Vf minus Vi. If it's compression work, W will be positive. That's because Vf will be less than Vi, and this expression in the bracket will be negative. Negative cancels out negative, then the work is positive. The change in internal energy in such a situation is Q plus W, which is equal to Q minus P delta V. Okay, to the fun part, an isothermal process. An isothermal process is a process that is being carried out at constant temperature. So constant temperature, that's delta T, is equal to 0. Remember that an ideal gas is the gas for which its internal energy is a function of temperature only. So if temperature does not change, delta U is equal to 0. So at constant temperature, delta U is equal to 0. If we recall from first law, delta U, which is Q plus W, and it's now equal to 0, then Q is equal to negative of the work done. So all heat supplied is used as work, or all forms of work done on the system is converted to heat. There is no change in internal energy. Now, if in an isothermal process a small change is being considered, then we have our dW being equal to minus P dV. We take the integral of both sides. W reversible will be integral negative of the integral of V1 from state 1 to V2 to the final state after the process, multiplied by P delta V. Because it's a very slow process, and we said that in a slow process the properties of the system are not changing as much like a passive process, P cannot come out of the integral. It's not a constant of volume. If it's maybe for an irreversible process, P will not vary, so it can come out of the integral, and this will just be like an expansion against a constant process. So for an ideal gas, there's a relationship between pressure and volume. For an ideal gas, we talked about the equation of states, PV equals nRT. So P can be nRT over V. So the work done, which was given as the negative of the integral from state V1 to V2 of P dV. So P, we substitute for P, that's nRT. N, R, and T are constants. Number of moles is a closed system, so it's constant. R is the gas constant. T is the temperature, and since we are considering an isothermal process, so it's also a constant. So it can come out of the integral as well. And then we have, but V is not constant, it's changing. So this stays inside the integral, 1 over V dV. So if we recall from calculus, the integral of 1 over x dx is ln x, well, plus c. So we have a definite one here. So that would be n minus nRT bracket ln v2. That's natural log of v2 minus natural log of v1. So we apply the laws of indices and logarithm. So we have that this is minus nRT natural log of v2 divided by v1. So this is the expression for work done reversibly in an isothermal process. We can apply Boyle's law, and then we have that this. So Boyle's law is a P1 V1 equals P2 V2. So applying Boyle's law, this becomes minus nRT ln P1 over P2. The major difference between a reversible and an irreversible work done, so this is expression for irreversible work, it's minus P, so it's just against a constant pressure. In a reversible work, it's the pressure is considered from the beginning to the end. So the area under the graph represents the work done. So more work is done in a reversible process than in an irreversible process. So in summary, in a free expansion, external P is 0 and work done is 0. In an isothermal process, delta T is 0 because it's an isothermal process, it's a constant temperature process. And because we're working for an ideal gas, we're dealing with ideal gas, please, this is 0 because it's an ideal gas. Our delta U is 0. And from the first law, Q equals minus W, so heat supplied is converted to work. The work done in an irreversible isothermal process is a minus P into V2 minus V1 bracket closed. And for a reversible isothermal process, the work done is minus nRT natural log of V2 over. Let's work a quick example. The question is, 1 mole of an ideal gas at 300 Kelvin is allowed to expand isothermally against a constant external pressure of 1 bar from a volume of 1 liter to a volume of 5 liters. What is the work done by the gas and the heat absorbed from the surrounding? So there's a second part of the equation. Find the work necessary to convert the gas back to its original volume and to determine if the process is reversible. And then if the work were to be carried out reversibly, what would the value be? Okay. So it's always a good idea to write out the parameters. 1 mole, N equals 1, temperature is 300 Kelvin, the pressure of 1 bar, that's 10 to 5 Pascal, an initial volume of 1 liter, and that's 10 to minus 3 meter cube, to a final volume of 5 liters, that's 5 times 10 to minus 3 meter cube. So the question is to calculate the work done and its flow. So since P is constant against a constant external pressure, the work done, it's an irreversible process, is simply negative V1 to V2. P external can come out, so we have P external into V2 minus V1, and